In the ground improvement techniques, let us discuss about the physical and chemical modification of soil. The objectives of soil stabilization are to improve one or more of the soil properties such as volume stability, strength, permeability and durability. The first property is volume stability. The variations in moisture content accelerate the volume instability, that is swell or shrink, in most of the clay soils. Seasonal and long-term moisture changes in an expansive clay soil, if uncontrolled, disrupt road surfaces, crack buildings, break underground pipes and cause great economic loss. The solutions to the volume change are based on converting the soil into a rigid mass or retarding the moisture movement within the soil. The methods to control volume change are pre-soaking, pre-loading, use of impervious membranes, chemical and thermal stabilization, etc. The method of retarding the moisture movement using impervious membrane is effective only when there is complete isolation of stabilized soil. The chemical and thermal stabilization require sophisticated equipment and skilled labor. Hence, preloading is a good alternative for volume stability. The next property is strength. The deformation of soil due to volume changes by moisture variation is similar to the deformation of soil under external loads. Therefore, the stabilization methods used to improve strength of the soil also improve its volume stability and vice versa. The common cause of low soil strength is due to poor drainage. The strength of soil is important for the construction of buildings, airfields, tunnels, etc., which can be improved by improving the density of soil. The common methods to improve the density of soil are compaction, vibroflotation, sand piles, lateral consolidation, and using additives. Other methods to improve strength are chemical and thermal stabilization. Densification is always useful in improving soil strength. Even other stabilization method is employed. The next soil property is permeability. Inadequate pore pressure dissipation causes slip failures in earthworks. High seepage pressure causes tunneling, and low permeability of subgrade soil causes failure of roads and pavements. In regions of intermittent rainfall, perched water table can form above the impermeable clay layer, which causes trouble during construction. High permeabilities can be reduced by compaction, grouts, and using deflocculants such as polyphosphates. The low permeability of a soil can be increased by adding flocculants such as lime and gypsum. The stabilization method employed for altering the permeability need not improve its strength and volume stability. Let's discuss about the next soil property, that is durability. Durability of soil is its resistance against weathering process, erosion and traffic. The durability of soil is important for the design of roads, bridges, drainage ways, etc., as the poor durability leads to high maintenance cost. In stabilized soil, the poor durability is mainly due to wrong choice of stabilizer, insufficient stabilizer, or inadequate water or chemical resistance of soil. There is no proper test procedure to estimate the durability, but repeated loading and unloading tests may help to some extent. Wind-blown dust of unpaved roads or village roads can also be considered as the problem of durability. The temporary methods to suppress the dust include spraying of bituminous sprays, calcium chloride sprays, sodium chloride sprays, etc. The permanent methods are surface sealing, grass cover over the site, etc. Poor chemical durability in cement stabilized soil is due to the presence of sulfates in the soil. The parameters influencing the soil stabilization are gradation, mineralogy, admixtures, method of stabilization, and environmental conditions. Before selecting the stabilization technique, the colors of the soil and the water nearby surface pools at the site are to be observed. The soil type can be identified by field tests such as dilatancy test, dry strength test, immersion crumb test, etc. In soil stabilization, by using chemical and waste stabilizers, the soil properties are improved by blending of soil particles by mixing other materials. Soil stabilization depends mainly on chemical reactions between stabilizer and soil minerals to achieve the desired effect. The commonly used stabilizers are lime, cement, bitumen, fly ash, ground granulated, blast furnace slag, rice ash, sulfonated oils, potassium compounds, ammonium chloride, enzymes, polymers, etc. Now let us discuss about the lime stabilization. It is the oldest and commonly used chemical stabilization for clayey soils. The major compounds in Portland cement are calcium silicates, calcium aluminate and calcium aluminoferrite, which react with water to form cementitious compounds. Most of the soils contain silica and aluminosilicates, which facilitate to form cementitious compounds when lime is added. But for some soils where free silica is not available, it may be necessary to add siliceous materials to accelerate the reactions. The various forms of lime materials are quick lime, hydrated lime, dolomitic quick lime, monohydrated dolomitic lime and pressure hydrated dolomitic lime. The appropriate form of lime is used based on the availability of the material at the site and the soil conditions. Lime is obtained from limestone by heating above 1000 degrees centigrade, which is an endothermic reaction. Quicklime, when reacted with water, forms calcium hydroxide, which is an exothermic reaction. The most common impurity in lime is magnesium. Lime containing magnesium is called dolomitic lime or impure lime. When dolomitic lime is heated, dolomitic quicklime is formed. The reaction between dolomitic quicklime and water under normal atmospheric pressure conditions facilitates the hydration of calcium oxide fraction in the compound, and the resulting compound of lime is called monohydrated dolomitic lime. If the same reaction is occurred under additional pressure, the magnesium oxide fraction of dolomitic lime will also get hydrated and produce a compound called pressure hydrated dolomitic lime. The water affinity and heat exerted during hydration decreases with increase in magnesium content in the lime. Now let us see the soil lime reactions. When lime is added to the soil containing free silica, 4 important chemical reactions take place in the presence of water. They are cation exchange, flocculation, pozzolanic reaction and carbonation. First we will see the cation exchange. This reaction happens due to replacement of monovalent cations like sodium, hydrogen, potassium of soil by divalent calcium cations of lime. This reaction binds clay particles, resulting in reduction of liquid limit and thus plasticity. The plastic limit of soil increases with the addition of lime content and becomes constant after a certain point. This point is called lime fixation point. So the definition of lime fixation point is the amount of lime required to replace the existing monovalent cations of clay by divalent calcium cations of the lime is called lime fixation point. The plastic limit increases with lime content up to this point and becomes constant. This indicates that additional lime beyond this point will not contribute to cation exchange. At this point, the soil becomes saturated with calcium cations. But the addition of lime beyond this lime fixation point contributes to increase in strength. Next reaction is flocculation. After the cation exchange, the size of particles increases due to reduction in double layer thickness, which results in flocculation. In the flocculated structure, the size of voids increases and water holding capacity of soil increases, resulting in increase of liquid limit. The plastic limit of the soil also increases, and the increase in plastic limit is more than the increase in liquid limit, which causes reduction in the plasticity index. The flocculation and cation exchange improves the workability of soil due to reduction in plasticity. These two reactions, that is the cation exchange and flocculation, are combinedly called as soil modification. Next one is pozzolanic reactions. The reaction between the silica present in the soil and calcium in the lime along with water to produce cementitious compounds is a pozzolanic reaction. Hydration is a quick reaction, whereas pozzolanic reactions may continue for many years as they depend on the moisture and temperature conditions. Lime contents more than lime fixation point contributes to the development of calcium silicate hydrate gel, which is a natural tobermoate gel. This indicates the initiation of pozzolanic reactions. As the pH of the system increases, that means if the pH value is greater than 7, the silica present in the soil starts dissolving and calcium hydroxide dissociates into calcium and hydroxyl ions. These hydroxyls are taken away by silicon ions and the stable calcium silicate hydrate gel is formed. This gel spreads into the soil, occupies all the voids, binds the particles and causes cementation of particles. The reactions continue to separate hydroxyl ions till the equilibrium is reached. At the pH value of 12.6, complete dissociation of calcium hydroxide occurs. There is a continuous rise in the unconfined compressive strength of soil with lime content up to a certain lime content, and with further addition the strength remains constant. This is due to complete consumption of silica existing in the soil. The quantity of lime required for complete consumption of free silica present in the soil is called optimum lime content. Hence, the reactive silica in the soil mass is a more influencing factor than the quantity of lime that is added to the soil. After cementation, these three processes, that is cation exchange, flocculation and pozzolanic reactions, are combinedly called as soil stabilization, which increases the workability and strength of soil and decreases its plasticity and swell. Now let us see how to find the optimum lime content. Silica consumption in the soil for pozzolanic reactions depend on the amount of amorphous or free silica present in the soil. If the soil is having a crystallized form of silica, then it won't participate in pozzolanic reactions. The lime addition after complete consumption of silica will not increase the strength of soil. If you want to increase the strength beyond the optimum lime content, the compactive effort or temperature or solubility of silica should be increased. This optimum lime content can be estimated by plotting graphs for lime content versus plasticity index, or lime content versus pH, or lime content versus unconfined compressive strength. When the increase or decrease in the plasticity index, pH, or unconfined compressive strength diminishes with addition of lime content, the corresponding lime content can be taken as optimum lime content. Next reaction is carbonation. It is an undesirable reaction that occurs when the calcium ions react with carbon dioxide present in the air or in the soil and calcium carbonate is formed. So the calcium carbonate is a plastic material, that is weak cementing agent, which increases plasticity of soil and retard the pozzolanic reactions by binding the lime. The main reasons for carbonation during lime treatment are inadequate quantity of reactive silica in soil or addition of excess lime content beyond the optimum value. So to avoid the carbonation, the lime content should be estimated based on the free silica, that is reactive silica present in the soil. Next topic is parameters influencing lime stabilization. In that, first one is soil type. The lime reacts more quickly with montmorillonite clays than kyanite clays. Therefore, it is suitable for heavy clays. Lime stabilization is less effective for silts and not suitable for sands and organic soils. The lime stabilization is not appropriate for sands because in sands the silica content is in the crystallized form. If a soil does not possess enough reactive silica or free silica, it can be supplemented in the form of volcanic ashes or fly ashes. The second parameter is amount and form of lime. The soil with low pH values, that is pH value less than 7, requires additional lime to neutralize the acid. The minimum amount of lime required for soil modification is corresponding to the lime fixation point, that is to improve the workability of soil. After this point, the increase in lime content contributes to the formation of calcium silicate hydrate gel, which improves the strength of cementation of particles. The quantity of lime required for soil stabilization is corresponding to optimum lime content, that is to increase the strength. The form of lime depends on the availability of materials at the site and also the soil conditions. Next parameter is water content. Potable water is required for the process of mixing. If the soil water content at the site is more than that required for reactions, quick lime can be added. If the water content is less, hydrated lime is preferred. If the quick lime is only available at the site and the natural water content of the soil is below 50%, then mixing of additional water is essential for hydration. Next parameter is curing period. Hydration is a quick process, whereas pozzolanic reactions are time and temperature dependent. The unconfined compressive strength of soil lime mixture increases with curing period. During the curing period, with the addition of water, the repulsive force decreases and density increases. If all the repulsive forces are removed, pore water pressure increases and density decreases. The last parameter is environmental conditions. An acidic soil requires more lime content. The organic material present in the soil hinders the formations of calcium silicate hydrate gel by immobilizing calcium cations. If sulfates are present in the soil, they may react with calcium and carbonate of lime and form compounds such as yttringite and thermosite, which are expansive in nature. So, due to these compounds, the treated soil will be subjected to excess swelling than that of untreated soil. Further, the pH of the soil system also reduces, which constrains the development of pozzolanic products. With the increase in temperature, the pozzolanic reactions increases, solubility of calcium hydroxide decreases, but solubility of silicon dioxide increases. Now let us see the effect of lime addition on soil properties. First one is effect on index properties. The specific gravity of the lime amended soil decreases because of the addition of low specific gravity material to the soil, that is lime. The changes in liquid limit with the lime addition depend on the quantity of monovalent or divalent cations possessed by the soil. If the original clay is having divalent cations, there will be no consumption of divalent calcium cations of lime. The flocculation of soil starts without cation exchange, and due to flocculation, the liquid limit increases. If the clay is having monovalent cations like sodium and hydrogen, due to cation exchange, the water content of the soil reduces and the liquid limit decreases. When the reduction in the liquid limit due to cation exchange is balanced by the increase in liquid limit by flocculation, there is no effect on the liquid limit. For kylenetic clay, since it is already flocculated, no effect on liquid limit with lime. The number of monovalent cations in the soil influences the cation exchange capacity. The plastic and shrinkage limits of soil always increases with the addition of lime to the soil due to flocculation, because a higher shrinkage limit indicates less shrinkage of soil. The plasticity index of soil always decreases. Even if the liquid limit increases, the increase in plastic limit is much more than the increase in liquid limit, and hence the plasticity index always decreases. Effect on volume change behavior. With the addition of lime, the diffuse double layer thickness in expansive soil decreases and the consequent cementation of particles takes place. This causes binding of soil particles and reduction in swell and shrink behavior. Effect on compaction. So here the compaction curves of lime treated and untreated soil are compared. Here we can observe that the density of lime treated soil decreases and its optimum moisture content increases. For any soil, the curve on the wet side of optimum is always flatter than on the dry side. The wet side curve of lime treated soil is flatter than the untreated soil. The curve is broader and indicates resistance to compaction effort due to flocculated structure. The curve becomes more flatter with curing. Next one is effect on consolidation. The amount of pressure required to reduce the increase in void ratio due to swelling of an over-consolidated clay is called swelling pressure. By comparing the E log P curves of treated and untreated soils, it can be observed that the swell pressure and swell potential of treated soil are reduced. This is because of the reduction in water affinity for the calcium saturated lime treated soil and the cementitious matrix formed by lime addition, which resists the volumetric expansion. Next one is effect on strength. For the lime treated soils, the unconfined compressive strength rises up to optimum lime content, and it also increases with curing period. Lime addition to soil causes a significant increase in cohesion and a minor increase in angle of internal friction. The California bearing ratio of the soil also increases with lime addition. Next one is effect on stress strain characteristics. For soil lime mixtures, the lime addition increases the failure stress but decreases the ultimate strain when compared with the untreated soil. The fatigue stress decreases with lime stabilization and causes increase in the fatigue life and durability of the soil. Now let us see the lime application methods. That first one is surface application. In this application method, the soil is plowed and lime is applied or dispersed using a spreader. It is mixed with pulvimixers and then compacted using tamping or pneumatic type roller. But it is difficult to mix soils deeper than 300 millimeter. Next one is lime columns. The lime columns are similar to sand columns or drains, which are widely used for reducing the settlements. The boreholes of diameter around 0.5 meter are drilled in a pattern to a depth of about 10 meter, and the lime is forced into the soil using mixing tools. The lime columns reduce the settlements and can be used as foundations for lightweight structures. Next one is the lime piles. Lime piles are widely used for compacting saturated soils. They are prepared by drilling boreholes of around 15 cm diameter up to a depth of 5 to 8 meter with a spacing of 1.5 to 2.5 meter center to center. The boreholes are then filled with quicklime and the casing is removed. When lime reactions taken place in the soil, a large amount of heat is released and the pore water in the soil evaporates. The lime piles accelerate the consolidation of soil and increases its shear strength. Next one is jet grouting method. To fill the lime slurry in narrow areas or deep cracks, the quicklime is injected through a nozzle pipe with pressure, which is called jet grouting method. So where and all we can use this lime stabilization technique? The applications of lime stabilization includes subgrade and subbase stabilization, drying of soil, stabilizing embankment and canal lining, and foundation improvement. That first one is subgrade and subbase stabilization. So the lime stabilization technique is used to lower the plasticity or swell or moisture holding capacity and or to improve the stability. Next one is drying of soil. It can be used for drying of the soil for the construction of a site after rainfall. Then next one is stabilizing embankments and canal lining. So here lime stabilization is used to enhance the strength of embankments which carry roads or railways and slopes. The next one is foundation improvement. So lime stabilization is used for expansive soils to minimize the shrinkage, swelling and settlement. The stabilization of soil with the cement and bitumen will be discussed in the next session.